Before we talk about galaxies, before we talk about time, before we talk about James Webb itself, we need to confront a quiet lie that almost all of us grew up believing, a lie so comfortable that we never questioned it. Because from the ground, from classrooms, from textbooks, and from older telescopes, the universe appeared vast but understandable, enormous but mapped, mysterious but fundamentally under control. For decades, we were told a story where the universe had a beginning, expanded politely, formed galaxies slowly, and settled into something that scientists could more or less measure and describe, a story where humanity stood near the edge of knowledge but could still see the outline of the whole. The night sky reinforced that illusion, because when you look up, it feels crowded, it feels busy, it feels like everything is already there, already visible, already counted. Stars scatter across the darkness, the Milky Way stretches overhead, and the mind instinctively compresses all of that into something finite, something graspable. Even the word universe sounds contained, like a room with walls. And for a long time, science unknowingly encouraged that feeling, not out of arrogance, but out of limitation. Because every telescope before James Webb was trapped inside a narrow window of reality, able to see only what light had not yet been stretched, diluted, or hidden by time itself. We thought we were looking at the universe, when in truth, we were looking at a thin, curated slice of it, the parts that were loud enough, young enough, and close enough to announce their presence. Everything else was silent, invisible, and therefore assumed to be absent. That assumption shaped everything we believed about scale. It shaped how big we thought the universe was. It shaped how quickly we thought galaxies could form. It shaped how rare complexity should be in the early cosmos. And most importantly, it shaped how comfortable we felt inside existence itself. Then, James Webb opened its eye.
I have been waiting my entire astronomy career for JWST.
Not all at once. Not dramatically, quietly, methodically, patiently. And what it began to reveal was not a correction of small details, but a fundamental rupture in perspective. Because Webb did not simply add more dots to our maps, it showed that the map itself was wrong. Galaxies appeared where no galaxies should exist. Light arrived that should have faded into nothingness billions of years ago. Structures emerged that looked too large, too mature, too organized for a universe that young. And suddenly, the illusion began to crack. Because if galaxies existed earlier than expected, and in greater numbers than predicted, then the universe was not only bigger than we thought, it was bigger earlier than we thought, which is far more disturbing. Size alone can be adjusted. Timelines breaking cannot. When scientists first began analyzing Webb's deepest images, many assumed errors, calibration issues, misinterpretations, because the alternative was uncomfortable. The alternative was that the early universe was not sparse and chaotic, but crowded and efficient, assembling massive systems with alarming speed. That realization forces a question that lingers beneath every Webb discovery, a question that does not feel scientific at first, but deeply human, which is this: if the universe was already this large and structured when time itself was young, then how much of it have we never seen at all? The comforting idea that we live in a universe whose boundaries we can at least approximate begins to dissolve, replaced by something far colder and far more honest. The observable universe, the sphere of everything we can see, is not the universe. It is only the portion of reality whose light has had time to reach us. Beyond that boundary is not emptiness, but continuation, expansion, and structures permanently sealed away by the speed of light and the stretching of space itself. James Webb did not create this boundary, but it revealed how misleading it is. Because the deeper Webb looks, the more it becomes clear that the universe does not taper off gently into darkness, but explodes outward into unimaginable abundance. Galaxies are not rare islands in a cosmic ocean. They are everywhere, stacked in layers of time, packed into regions we assumed were empty. growing, colliding, and evolving far faster than our models ever allowed. This is where the scale becomes terrifying, not because it is large, but because it is uncontrollable. You cannot point to an edge. You cannot gesture to a final structure. You cannot even be sure that what you see represents the average. Webb suggests that what we observe may be the bare minimum, the quietest version of reality, filtered through distance and expansion until only the most resilient light survives. And if that is true, then the universe is not just bigger than expected, it is fundamentally misjudged. Everything we thought was distant may be local. Everything we thought was early may be late. Everything we thought was rare may be common. This is why Webb's revelations feel unsettling rather than celebratory, because they do not simply add wonder, they subtract certainty. They take away the comfort of thinking that humanity arrived late to a quiet cosmos. Instead, they hint that we emerged inside something already vast, already complex, already overwhelming. And this is only the beginning, because the deeper Webb looks, the more it becomes clear that space is not a backdrop, but a time machine, and that every photon it captures carries a story distorted by expansion, stretched by redshift, and altered by forces we barely understand. To make sense of what Webb is showing us, we must abandon the idea that distance is simple, and accept that looking far away is the same as looking long ago, and that the universe we see is not frozen in one moment, but layered like sediment across time. That realization pulls us forward into the next chapter, because to understand why Webb's discoveries are so disruptive, we first need to understand how it sees the universe at all, how light becomes history, how space stretches memory, and why every deep image from Webb is not just a photograph, but a fragment of the universe's past reaching us long after it was never meant to be seen. James Webb does not look at the universe the way our eyes do, and that difference is the reason everything we thought we understood is starting to unravel, because when you look up at the night sky, you are not seeing distance, you are seeing delay, and Webb was built specifically to exploit that delay in ways no telescope before it ever could. Every point of light you see is not where it is now, but where it was when that light began its journey, a journey that can take millions or even billions of years, meaning space is not a snapshot of reality but a layered archive of time itself. Older telescopes like Hubble could peer deep into space, but they were limited by the kind of light they could see, trapped mostly in visible wavelengths that fade and disappear as the universe expands. James Webb, by contrast, was designed to see in infrared, a range of light that stretches as the universe stretches, carrying ancient information forward instead of letting it vanish. This is the critical shift that changes everything, because as the universe expands, light traveling through it gets stretched into longer, redder wavelengths, a phenomenon known as redshift, and the farther that light travels, the more extreme that stretching becomes. By the time light from the first galaxies reaches us, it has been pulled far beyond the visible spectrum, invisible to telescopes that were never meant to catch it. For decades, we assumed that meant those early galaxies were dim, small, and rare, when in reality we simply lacked the ability to see them at all. James Webb was built like a time hunter, its massive gold-coated mirror, designed to collect faint infrared photons that have been drifting since the universe was young. Photons that carry information from an era when stars were first igniting, and galaxies were assembling themselves in ways we barely understand. When Webb looks at a distant galaxy, it is not seeing that galaxy as it exists today, but as it existed billions of years ago, sometimes just a few 100 million years after the Big Bang. This is where the scale becomes unsettling, because Webb is not just extending our vision outward, it is peeling back layers of cosmic history, revealing that the early universe was already busy, crowded, and unexpectedly mature. The deeper Webb looks, the further back in time it goes, and instead of finding darkness and emptiness, it finds structure, brightness, and complexity that should not be there according to our old models. This creates a profound tension between what the math predicted and what the universe is actually showing us. Scientists expected the earliest galaxies to be small, faint, and chaotic, collections of stars slowly clumping together over time. What Webb is seeing instead are galaxies that appear massive, organized, and luminous, at an age when the universe should barely have had time to cool. To understand why this is shocking, you have to understand how unforgiving cosmic timelines are. After the Big Bang, the universe expanded rapidly, cooling as it went, and it took hundreds of millions of years just for the first stars to form. Those stars then had to live and die to seed heavier elements, which are necessary for building complex structures like galaxies. According to this sequence, large, bright galaxies should take billions of years to assemble, and yet Webb is seeing them when the universe was still in its infancy. This suggests one of two unsettling possibilities. Either galaxies formed far faster than our physics allows, or our understanding of early cosmic evolution is incomplete at a foundational level. Webb's infrared vision does more than reveal ancient objects, it exposes the bias baked into our previous observations. We were never seeing the full universe, only the parts that cooperated with our limitations. The universe did not suddenly become larger. When Webb launched, it was always this large, we were just blind to most of it. This is why Webb's images feel less like discoveries and more like revelations, because they force us to confront how much of reality was hidden simply because we lacked the right eyes. Every deep-field image from Webb is a confrontation with our ignorance, showing galaxies layered behind galaxies, stretching so far back that time itself becomes difficult to imagine. And this layering matters, because it means that when we look deep into space, we are not looking at one universe, but many versions of the universe stacked together, each frozen, at a different moment in its evolution. The nearest galaxies are relatively recent, the farthest are ancient. In between is a continuous gradient of cosmic history, all arriving at our detectors at the same time. This turns Webb into a kind of cosmic archaeologist, excavating the universe not by digging deeper into space, but by reaching further back into time. And the deeper it goes, the more it suggests that the early universe was not a quiet beginning followed by slow growth, but a violent, productive era that wasted no time building complexity. This realization sets up an even more disturbing question, because if light from the earliest galaxies can reach us, then there must be even more light that never will. The observable universe is defined not by how far the universe extends, but by how far light has had time to travel since the Big Bang. Beyond that boundary is a vast region of reality forever hidden from us, expanding away faster than light can cross the gap. James Webb does not break this limit, but it brings us uncomfortably close to it, showing us the edge of what is knowable. And the closer we get to that edge, the clearer it becomes that the universe does not slow down or thin out near the horizon. It continues, likely with the same density of galaxies, the same complexity, and the same chaos, just permanently unreachable. This reframes our place in the cosmos in a way that is hard to emotionally process. We are not at the center of a vast but comprehensible structure. We are inside a small bubble of visibility, surrounded by an ocean of reality we can never access. Webb's ability to see ancient light does not make the universe feel more familiar, it makes it feel more alien, because it reveals how little of it we will ever truly know. And as Webb keeps pushing deeper, capturing light from earlier and earlier times, it sets the stage for the next revelation, because ancient light does not just show us old galaxies, it exposes behaviors and brightness levels that defy our expectations, leading directly into the next chapter, where we confront the most disturbing discovery of all: ancient galaxies that shine too brightly, grow too fast, and exist in numbers that suggest the universe was never as empty or as simple as we were led to believe. What disturbed scientists was not just that James Webb was seeing farther than any telescope before it, but that what it was seeing at those extreme distances simply should not exist in the way it does, because light from the earliest epochs of the universe was never supposed to look like this. According to everything we thought we understood, the first few 100 million years after the Big Bang should have been a dim, transitional era, a time when matter was only beginning to organize, when the first stars flickered weakly inside small, chaotic proto-galaxies, and when brightness itself should have been scarce. Instead, Webb began detecting ancient light that was shockingly intense, coming from galaxies that appeared too luminous, too massive, and too well structured for their age. These were not faint smudges, barely clinging to existence. These were bright, confident systems, radiating enormous amounts of energy at a time when the universe should still have been learning how to shine. The problem was not subtle. It was immediate and deeply uncomfortable. When astronomers calculate how bright a galaxy should be, they rely on models of star formation, gas cooling, and the availability of heavy elements, all of which take time to develop. Early galaxies should lack metals. Their stars should be massive but short-lived. Their total light output should be limited. And yet, Webb's observations kept revealing galaxies whose brightness rivaled much older systems, as if the universe had skipped several developmental steps entirely. At first, scientists questioned the data. Calibration errors were considered. Misidentifications were suspected. Perhaps these galaxies were closer than they appeared. Perhaps their redshifts were being misread. But as independent analyses piled up, the pattern refused to go away. Different teams, different methods. Same conclusion. The ancient universe was brighter than it had any right to be. This is where the tension deepens, because brightness is not just a visual property. It is a record of activity. Bright galaxies imply large numbers of stars forming rapidly. They imply dense regions of matter collapsing efficiently. They imply a universe that was extraordinarily productive at an age when productivity should have been limited by physics itself. In simple terms, the early universe was acting like it was already old. This forces a reevaluation of cosmic timelines, because if galaxies reached maturity so quickly, then either the universe evolved far faster than our theories allow, or something fundamental about those theories is missing. Neither option is comfortable. Speeding up cosmic evolution breaks our understanding of gravity, cooling, and feedback processes. Adding missing ingredients implies there are forces or behaviors we have not yet accounted for. And lurking beneath both possibilities is a more unsettling implication, which is that the universe may not be following the neat, orderly narrative we constructed for it. The ancient light Webb is capturing is not just old, it is stretched, distorted, and filtered by billions of years of expansion, meaning what we see is already a softened version of reality. If even that softened signal is this bright, then the original galaxies must have been even more extreme. This leads to a quiet but profound question, which is whether the early universe was fundamentally different in character, not just degree. Perhaps star formation was more efficient. Perhaps dark matter behaved differently. Perhaps the first structures formed under conditions we no longer observe. Webb does not answer these questions, it exposes them, and exposure is destabilizing. It forces scientists to confront the possibility that the universe's earliest chapter was not a gentle emergence, but a rapid, almost aggressive explosion of structure. The phrase "shouldn't exist" is not used lightly in science, but these galaxies push dangerously close to that boundary. They occupy a space where models begin to strain, where explanations feel forced, and where uncertainty grows instead of shrinking. And the deeper Webb looks, the more examples it finds. This is not a single anomaly. It is a population, a pattern. A hint that what we thought was rare may be common, and what we thought was delayed may have been immediate. The ancient universe, according to Webb, was not waiting around. It was building. This realization has cascading consequences, because if early galaxies formed faster and brighter than expected, then the total number of galaxies in the universe may be far higher than previous estimates. It also means that the mass distribution of the universe may be skewed toward complexity far earlier than assumed. This directly feeds into the terrifying scale problem, because brightness allows detection, and detection implies abundance. Webb is not just finding individual surprises. It is suggesting that the universe is packed with structure, all the way back to its earliest observable moments. This shatters the comforting idea that complexity emerged slowly and sparsely, leaving long stretches of emptiness behind. Instead, it paints a picture of a universe that filled itself quickly, densely, and relentlessly. And if that is true within the observable universe, then what lies beyond the observable boundary becomes even more unsettling, because there is no reason to believe the universe suddenly changes character at the edge of what we can see. If ancient galaxies are abundant here, they are likely abundant everywhere. The light Webb detects is a messenger from a past that refuses to align with our expectations, and every new data release tightens the pressure. Scientists are now forced to revise models, introduce new parameters, and consider alternative pathways for early cosmic growth. This is how scientific revolutions actually happen, not with explosions, but with persistent discomfort, with data that will not cooperate, with observations that refuse to be explained away. The terrifying part is not that the universe is larger than we thought. It is that it appears to have been powerful, active, and complex from the very beginning, leaving us to wonder whether our presence is late, incidental, and small, in ways we have barely begun to process. And this naturally leads to the next question, because brightness and abundance are symptoms, not causes. Something had to organize matter this efficiently. Something had to hold these early galaxies together. Something unseen had to provide structure before stars could even form. And that pulls us forward into the next chapter, where the story shifts from what Webb sees to what Webb cannot see, the invisible architecture shaping the universe long before light ever arrived. The more scientists stared at the early universe through James Webb's eye, the harder it became to maintain the comforting narrative that the cosmos began simply and grew slowly. Because the evidence now suggested something far more unsettling, which was that complexity did not wait its turn. For decades, the standard picture of the early universe described a long, quiet childhood, a period after the Big Bang, where matter cooled, spread out, and gradually assembled into the first fragile stars and small proto-galaxies, structures that would then take billions of years to grow into the massive galaxies we see around us today. This picture made intuitive sense, because gravity works patiently, stars take time to form, and feedback from radiation and supernovae should slow growth rather than accelerate it. The universe, according to this view, was cautious and inefficient at first. James Webb is now showing us that this story may be fundamentally wrong. Instead of a sparse and hesitant beginning, Webb reveals an early universe crowded with large, bright, surprisingly mature galaxies, appearing so soon after the Big Bang that their very existence strains the timeline of cosmic evolution. These galaxies do not look like primitive sketches, they look like finished structures. They have defined shapes, they contain enormous numbers of stars. They shine with an intensity that implies rapid, efficient star formation on a scale that should not have been possible so early. This forces scientists to confront a deeply uncomfortable possibility, which is that the early universe was not small in any meaningful sense, nor was it simple. It was already busy, already productive, already assembling large-scale structure at a pace that defies our expectations. When we say the early universe was small, we usually mean it was young, but youth does not necessarily imply simplicity, and Webb's observations are exposing how misleading that assumption has been. Even a few 100 million years after the Big Bang, the universe appears to have been capable of producing complexity at breathtaking speed. This does not just challenge details of existing models, it challenges their underlying philosophy. Many cosmological theories are built on gradualism, the idea that large, ordered structures emerge slowly from smaller, chaotic ones. Webb is hinting that the universe may have skipped steps, leaping from near uniformity to complexity far faster than we thought possible. This raises a series of cascading questions that ripple through cosmology. How did gas cool so efficiently in the early universe? How did gravity overcome radiation pressure so quickly? How did stars form in such enormous numbers without tearing their galaxies apart? How did feedback processes fail to regulate growth as expected? Each question points toward missing physics, incomplete assumptions, or oversimplified models. One possibility is that star formation in the early universe was fundamentally different from star formation today, operating under conditions of density, temperature, and composition that allowed matter to collapse and ignite with unprecedented efficiency. Another possibility is that dark matter halos formed earlier and more densely than predicted, providing deep gravitational wells that accelerated galaxy growth. Yet another possibility is that our measurements of mass and brightness are being subtly misinterpreted, that ancient galaxies appear larger or brighter than they truly are due to effects we have not fully accounted for. But even the most conservative explanations struggle to fully erase the tension. The pattern remains. The early universe looks too grown up. This realization is unsettling because it undermines a key source of comfort in cosmology, which is the idea that complexity is rare and hard-won. Webb suggests that complexity may be the universe's default state rather than its exception. If galaxies formed quickly and abundantly from the very beginning, then the universe may have been primed for structure in ways we did not anticipate. This reframes the Big Bang not as a gentle release followed by a long wait, but as the opening act of a universe eager to organize itself. And if that is true, then the scale of the universe becomes even more terrifying, because rapid early growth implies not just more galaxies, but more galaxies earlier, filling space with structure long before we ever imagined it could. The implication is that by the time light from these early galaxies reaches us, the universe may already have been densely populated with massive systems, far beyond what we can detect. Our observable universe may represent only a thin slice of an already enormous cosmic population. This is where the emotional weight of Webb's discovery settles in, because it means we did not emerge into a quiet universe waiting to be explored. We emerged into a universe that was already vast, already complex, already far beyond our ability to comprehend in full. The early universe, once imagined as a simple starting point, now looks like a place of intense activity and rapid organization, where the seeds of everything we see today were planted with shocking speed. This also raises uncomfortable questions about the nature of cosmic order itself. If structure emerges this quickly, what does that say about the laws governing reality? Are they tuned toward complexity? Do they favor organization? Or are we witnessing a statistical fluke, amplified by our limited window of observation? James Webb does not answer these questions. It amplifies them. It forces us to accept that our mental image of the universe's infancy was shaped more by ignorance than by evidence. The early universe was not a blank canvas slowly filled in. It was a crowded workshop, producing galaxies at a pace that challenges our sense of causality and control. This realization strips away another layer of comfort, because it suggests that the universe did not need time to become overwhelming. It was overwhelming almost immediately. And if the universe could achieve this level of complexity so early, then its total scale, when extended across billions of years of expansion, becomes almost impossible to process. The problem is no longer just that the universe is large. The problem is that it may be far larger than any model built on slow growth can accommodate. This brings us to a critical turning point in the story, because once we accept that the early universe was neither small nor simple, we are forced to confront the consequences of that fact. If galaxies formed rapidly and abundantly at the dawn of time, then our estimates of how many galaxies exist and how much universe there truly is may be catastrophically low. The terrifying scale problem emerges not as a speculative idea, but as a logical consequence of Webb's observations. And it is that problem, the realization that the universe's true size may dwarf even our most extreme estimates, that pulls us forward into the next chapter, where we stop focusing on individual galaxies and confront the possibility that what we can see is only a tiny, misleading fragment of a cosmos far larger and more unreachable than we ever imagined. The terrifying realization that begins to settle, once James Webb's discoveries are taken seriously, is not about any single galaxy or any single observation, but about scale itself. Because when early galaxies appear too massive, too numerous, and too bright, the problem quietly stops being local and becomes universal. For decades, astronomers estimated the size and content of the universe by counting what they could see and then extrapolating outward, assuming that the visible portion of the cosmos was representative of the whole. This approach felt reasonable when galaxies appeared to form slowly and sparsely, because slow growth implies limits, and limits imply manageable totals. But Webb is now showing us that the early universe was anything but sparse, and that assumption collapses the moment abundance appears where scarcity was expected. If galaxies formed earlier and faster than predicted, then there was more structure present earlier in time, and if there was more structure earlier, then there has been more time for that structure to multiply, merge, and spread as the universe expanded. This creates a compounding effect, because early abundance does not just add galaxies, it multiplies possibilities. A universe that starts crowded becomes exponentially more crowded as time goes on. Suddenly, the comforting estimates of hundreds of billions of galaxies begin to feel like placeholders rather than conclusions. Some scientists now seriously consider the possibility that the observable universe alone may contain trillions of galaxies, not because someone changed a number arbitrarily, but because Webb is revealing populations of faint, distant galaxies that previous telescopes simply could not detect. Each new deep-field image shows more galaxies packed into tiny patches of sky than we ever expected, hinting that our cosmic census has been radically incomplete. The terrifying part is not just that there may be more galaxies, but that the observable universe itself may be an unrepresentative sample of a much larger whole. The observable universe is defined by a limit imposed by physics, not by the actual size of reality. It is the region of space from which light has had enough time to reach us since the Big Bang, and that region is shrinking in relevance as the universe expands faster and faster. Beyond that boundary is more universe, not emptiness, and there is no reason to believe it suddenly becomes simpler or less populated. If Webb is seeing unexpected abundance near the edge of what we can observe, then abundance likely continues beyond it, forever hidden from view. This is where the scale problem becomes existential rather than academic, because it means our mental image of the universe may be missing the vast majority of reality. The part we can see, measure, and model may be a thin shell floating inside something incomprehensibly larger. And unlike ignorance caused by lack of data, this ignorance is permanent. No future telescope, no matter how powerful, can see beyond the cosmic horizon. The expansion of space itself ensures that most of the universe will remain inaccessible forever. Webb does not overcome this limitation, but it brings us closer to it than ever before, forcing us to stare at the boundary and realize how misleading our previous comfort was. When scientists say the universe is expanding, it is tempting to imagine galaxies flying outward into pre-existing space, but what is actually happening is far stranger. Space itself is stretching, carrying galaxies along with it, and as that stretching accelerates due to dark energy, distant regions of the universe are being pushed away faster than light can bridge the gap. This means there are galaxies that exist right now, whose light will never reach Earth, not because they are too faint, but because space is expanding too fast. They are not hidden by distance alone, but by time itself. The observable universe is not growing to include them, it is shrinking relative to the whole. And this realization reframes Webb's discoveries in a deeply unsettling way, because the galaxies it reveals at extreme distances are not the edge of existence, but the edge of perception. They are the last messages we will ever receive from regions that are already slipping beyond causal contact. Every ancient galaxy Webb detects near the cosmic horizon is a reminder that we are watching the universe disappear in real time, not by vanishing, but by becoming unreachable. The scale problem, then, is not just about how big the universe is, but about how much of it is permanently lost to us. Webb's discoveries suggest that the universe was large and complex very early on, which implies that the total amount of structure beyond our horizon is likely staggering. There could be orders of magnitude more galaxies than we will ever know about, each with its own stars, planets, and histories, existing without any possibility of interaction with us. This is terrifying not because it diminishes humanity, but because it removes the illusion that knowledge can eventually catch up with reality. We are not climbing toward a complete picture. We are peering through a keyhole into something that has no obligation to reveal itself fully. The more Webb shows us, the clearer it becomes that the universe does not scale gently. It scales brutally. It does not grow in a way that preserves comprehension. It grows in a way that overwhelms it. Early abundance implies late excess. Late excess implies unreachable vastness. And unreachable vastness implies that most of reality will forever remain theoretical, inferred, and unseen. This forces cosmology into a new emotional posture, one where humility is not philosophical but necessary. Models can describe patterns within the observable universe, but they can no longer pretend to describe the universe itself. The distinction matters. When we say the universe is a certain size, we are really saying that the observable universe is a certain size, and Webb is making that qualifier impossible to ignore. The terrifying scale problem is not a flaw in science, but a consequence of success, because the better we see, the more obvious our limits become. James Webb did not make the universe larger. It revealed how small our window into it truly is. And as this realization settles, it sets the stage for an even more disturbing idea, because once we accept that most of the universe is hidden from us, we must confront why it is hidden, and what forces are responsible for shaping, stretching, and separating reality on these unimaginable scales, a question that pulls us forward into the next chapter, where the story shifts away from visible galaxies and into the unseen forces that dominate the cosmos, beginning with the invisible architecture that holds galaxies together and determines where structure can exist. Dark matter enters the story not as a dramatic reveal but as an unavoidable necessity, because once James Webb began showing galaxies forming earlier, faster, and in greater numbers than expected, the visible universe alone could no longer explain itself. Everything we see, every star, every glowing cloud of gas, every brilliant galaxy, accounts for only a small fraction of the universe's total mass, and this has been known for decades, but Webb's discoveries have turned that quiet fact into an urgent problem. Galaxies do not form in isolation. They need something to gather around, something massive enough to pull gas inward, and hold it together long enough for stars to ignite. Visible matter cannot do this job on its own, especially not in the early universe, where expansion was rapid and radiation pressure was intense. Without an invisible framework already in place, the galaxies Webb is observing simply should not exist in the form they do. This is where dark matter stops being a theoretical curiosity and becomes the silent architect of everything we see. Dark matter does not emit light, absorb light, or interact with normal matter in ways we can directly observe, but its gravitational influence is undeniable. It outweighs visible matter by a factor of roughly 5 to 1, meaning that most of the universe's mass is invisible, shaping reality without announcing itself. Long before the first stars ignited, dark matter began clumping together under gravity, forming vast halos that acted as gravitational wells. These halos became the scaffolding upon which galaxies could rapidly assemble, pulling gas inward, accelerating collapse, and allowing star formation to proceed far more efficiently than visible matter alone ever could. James Webb's observations strongly suggest that these dark matter structures were already in place extremely early, providing the framework needed for galaxies to grow fast and grow big. This is unsettling, because it means that the visible universe is only the surface expression of something far larger and far more dominant. The galaxies we see are not the main structure. They are decorations hung on an invisible frame. Webb is not directly seeing dark matter, but it is revealing its fingerprints everywhere, in the unexpected speed of galaxy formation, in the density of early cosmic structures, and in the way matter appears to have organized itself with ruthless efficiency. The terrifying implication is that most of the universe's architecture is fundamentally hidden from us, not because we lack imagination, but because it does not interact with light at all. We are living inside a universe whose primary structure is invisible, and Webb is forcing us to reckon with how little of reality we can actually observe. This invisible architecture does not just shape individual galaxies. It shapes the large-scale structure of the cosmos itself, determining where clusters form, where voids appear, and how matter flows across unimaginable distances. The universe, when mapped through simulations that include dark matter, resembles a vast cosmic web, with filaments stretching across space, intersecting at dense nodes where galaxies cluster, and surrounding enormous empty regions where little visible matter exists. This web is not poetic metaphor. It is a consequence of gravity acting on dark matter over billions of years. Webb's deep observations are now beginning to line up with these predictions in unsettling ways, suggesting that this cosmic web was already well developed when the universe was very young. That means structure did not slowly emerge from chaos. It snapped into place with alarming speed. This challenges our intuition about how order arises, because it implies that the universe is predisposed toward structure, guided by invisible mass that organizes reality from behind the scenes. The visible universe is not the foundation, it is the after effect. And this raises an uncomfortable philosophical question, which is whether what we call reality is merely the thin, luminous skin of something far deeper and far stranger. Dark matter dominates the universe's mass budget, but it remains one of the greatest mysteries in all of science. We do not know what it is made of. We do not know how it behaves beyond its gravitational influence. We do not know whether it is one thing or many. And yet, without it, the universe James Webb is revealing would not be possible. This creates a paradox where the most important component of cosmic structure is also the least understood. Webb's discoveries are tightening this paradox rather than resolving it, because they demand that dark matter be even more effective, more abundant, and more influential in the early universe than previously assumed. The galaxies Webb sees at extreme distances are not just evidence of early star formation. They are evidence that dark matter was already deeply organized, already shaping space, already dictating where matter could gather. This means that the terrifying scale of the universe is not just about size, but about dominance. Most of what exists does not shine. Most of what exists does not speak to us in photons. It shapes the universe silently, permanently, and beyond our direct perception. This realization strips away another layer of comfort, because it tells us that even within the observable universe, most of reality is inaccessible to our senses. We are not missing distant regions alone. We are missing the majority of what is right here. Dark matter does not care about observation. It does not reveal itself when looked at more closely. It remains hidden, even as our instruments improve. Webb can only infer its presence through consequences, through what would not exist without it, and those consequences are now everywhere. The early universe's unexpected maturity, its crowded nature, its rapid assembly, all point toward an invisible hand-guiding structure long before light could tell the story. This makes the universe feel less like an open book and more like a layered puzzle, where the visible pieces are only hints of a deeper order. And dark matter is not the end of this discomfort. It is only the beginning. Because if invisible matter can dominate structure, then invisible forces may dominate destiny. Dark matter holds galaxies together, but it does not explain why the universe is expanding the way it is, or why that expansion is accelerating. Webb's discoveries push us toward this next realization, because once we understand that most of the universe's unseen mass-shaping structure, we are forced to confront the even more disturbing force shaping its future. The universe is not just organized by invisible matter, it is being pulled apart by invisible energy. And to understand the full terror of the universe James Webb is revealing, we must move beyond what holds galaxies together and confront what is driving them away from each other faster and faster, leading directly into the next chapter, where the story shifts from structure to separation, from dark matter to dark energy, and from the universe's hidden architecture to its unstoppable expansion. Dark energy enters the story not as a solution but as an escalation, because once James Webb forces us to accept how structured, abundant, and rapidly assembled the universe is, we must also confront the force that is quietly undoing all of that structure at the largest scales. Dark energy is not something Webb sees directly, but it is something Webb's discoveries make impossible to ignore, because every distant galaxy Webb observes is not just far away in space and time, it is being carried away by the expansion of space itself. For most of the 20th century, scientists believed the universe's expansion, set in motion by the Big Bang, should be slowing down over time as gravity worked to pull matter back together. That belief felt intuitive, because gravity is attractive and matter is abundant. Then, in the late 1990s, astronomers made a discovery that shattered that intuition, finding that the expansion of the universe is not slowing down at all, but accelerating. Something unseen, something pervasive, something extraordinarily powerful is pushing space itself apart, and we have no clear idea what it is. This force was named dark energy, not because it is understood, but because it is mysterious, and Webb's observations are now giving that mystery a far more unsettling context. When Webb looks at ancient galaxies near the edge of the observable universe, it is seeing light that began its journey when the universe was much smaller, much denser, and much younger. Over billions of years, as that light traveled toward us, the space it moved through stretched, elongating the light's wavelength and diluting its energy. This stretching is not a side effect, it is the expansion of reality itself. And the farther away a galaxy is, the more its light has been stretched, the faster it is receding from us, and the more influence dark energy has had on its journey. Webb's ability to detect extremely distant galaxies means it is probing an era when dark energy was less dominant than it is today, offering a rare glimpse into how expansion has evolved over cosmic time. What scientists are beginning to realize is that dark energy is not just a late-stage phenomenon, gently pushing galaxies apart. It is a fundamental property of space that becomes more powerful as space grows. Unlike matter and radiation, which dilute as the universe expands, dark energy does not thin out. It remains constant per unit volume of space, meaning that as the universe expands and creates more space, the total amount of dark energy increases. This creates a feedback loop where expansion fuels more expansion, driving galaxies away from each other faster and faster. Webb's discoveries make this deeply unsettling, because the more galaxies we find at great distances, the more obvious it becomes that enormous portions of the universe are already beyond our reach, carried away by accelerated expansion into permanent isolation. The terrifying scale of the universe is not just about size, but about separation. It is about the realization that even within the observable universe, connectivity is temporary. Regions that were once causally connected are being torn apart by expansion, slipping beyond each other's horizons forever. James Webb is showing us galaxies whose light barely makes it to us before that connection is severed, like final messages arriving from regions that are already gone in every meaningful sense. This forces us to rethink what the observable universe actually represents. It is not a stable container of reality, it is a shrinking window. Over time, as expansion accelerates, fewer and fewer galaxies will remain visible from any given point. In the far future, observers in distant galaxies will see a much emptier sky, not because the universe has fewer galaxies, but because dark energy has pushed everything else beyond view. Webb's discoveries allow us to glimpse this process in reverse, seeing the universe when more was visible, when horizons were closer, when cosmic neighborhoods were larger. That contrast makes the future implications impossible to ignore. Dark energy ensures that the terrifying scale of the universe is not something we will ever fully map, because the map itself is being torn apart as we draw it. Even now, galaxies are crossing horizons beyond which their light will never reach us again. Entire regions of reality are vanishing from causal contact, not through destruction, but through expansion. This introduces a profound sense of cosmic isolation that goes beyond mere size. It is not just that the universe is large. It is that it is actively separating itself into disconnected islands, each trapped within its own observable bubble. Webb's observations suggest that the early universe was dense with structure, but dark energy guarantees that this density will not translate into long-term connection. The universe may be filled with galaxies, but most of them are already unreachable and will remain so forever. This realization reframes humanity's place in the cosmos in an unsettling way. We are not explorers standing at the edge of an infinite frontier waiting to be charted. We are observers inside a rapidly shrinking sphere of visibility, watching as the universe quietly removes itself from view. Dark energy does not announce its presence with explosions or light. It works silently, relentlessly, stretching space, thinning relationships, and ensuring that knowledge has a hard limit. Webb's discoveries intensify this discomfort because they reveal just how much is being lost. The more galaxies we find near the horizon, the more we realize how many lie beyond it, forever unseen. Dark energy transforms abundance into absence, not by destroying galaxies, but by hiding them behind the geometry of space-time itself. This leads to an almost philosophical terror, because it suggests that reality is not just vast, but selectively inaccessible. There is no technological solution to this problem. No telescope can outrun expansion. No future civilization can recover what has already slipped beyond the cosmic horizon. The universe is not only bigger than we imagined, it is actively denying us access to most of itself. And yet, this separation does not happen randomly. It follows the invisible structure laid down by dark matter, meaning that the universe's growth and its fragmentation are intertwined. Dark matter builds structure. Dark energy dissolves connection. Together they define the universe James Webb is revealing, a cosmos that is at once richly structured and fundamentally isolating. This duality is what makes the scale terrifying rather than merely impressive. We are surrounded by galaxies, yet cut off from nearly all of them. We exist in a universe that overflows with complexity, yet withholds most of it forever. As Webb continues to push deeper, it does not just show us where galaxies are. It shows us where they are going, and more importantly, where we can never follow. This realization pulls us into the next chapter, because once we accept that dark energy is accelerating separation and hiding vast regions of reality, we must confront the final consequence of that process, which is the existence of trillions of galaxies that will forever remain beyond observation, unreachable not because they do not exist, but because the universe itself will not allow us to see them, a truth that brings the terrifying scale of the cosmos fully into focus. As the implications of dark energy settle in, the universe revealed by James Webb begins to feel not just vast, but actively unreachable. Because accelerated expansion does more than stretch space, it redraws the boundaries of reality itself. There is a limit to what any observer can ever see, a boundary defined not by technology or effort, but by physics, and that boundary is known as the cosmic horizon. The cosmic horizon is not a physical wall or an edge in space, but a limit in time, the maximum distance from which light has had enough time to reach an observer since the beginning of the universe. Everything beyond that horizon exists, but it exists without the possibility of interaction. Its light will never arrive, its signals will never be received, its events will never be known. This is not speculation. It is a consequence of expansion, and James Webb is now showing us just how close we already are to that boundary. When Webb detects extremely distant galaxies, it is seeing light that began its journey when the universe was young, and has spent billions of years fighting against the stretching of space to reach us. Some of that light barely makes it. Some of it arrives stretched to the edge of detectability, and beyond those galaxies are countless others whose light will never arrive at all, not because it is too faint, but because space itself is expanding faster than light can cross it. This realization transforms the observable universe from a comforting concept into a trap, because the observable universe is not a representative sample of reality, but a shrinking bubble carved out by time and expansion. It is the region of the universe we are temporarily allowed to know, and that permission is being slowly revoked. As dark energy accelerates expansion, more and more regions of space cross beyond our cosmic horizon, becoming permanently inaccessible. This means that the observable universe was larger in the past than it will be in the future. Webb's deep observations are therefore not just explorations, but rescues, capturing the last light we will ever receive from regions that are already slipping away. Every ancient galaxy Webb observes near the edge of detectability is a farewell, a final whisper from a part of the universe that is disappearing from causal contact. This makes Webb's discoveries feel haunting rather than triumphant, because they reveal not just what exists, but what we are losing. The terrifying scale of the universe is inseparable from this loss, because it tells us that most of reality will never be observed, not now, not later, not ever. Even if humanity survives for billions of years and builds instruments beyond our imagination, the cosmic horizon will remain. No amount of intelligence can outrun the geometry of spacetime. The universe is not hiding its full size out of secrecy. It is hiding it out of inevitability. And James Webb, by pushing us so close to that boundary, makes this inevitability impossible to ignore. The deeper we look, the more obvious it becomes that the observable universe is a biased sample, skewed toward what was close enough, bright enough, and early enough to be seen before expansion pulled everything apart. This bias matters deeply because it means our theories of cosmology are built on incomplete data by definition. We can infer what lies beyond the horizon, but we can never verify it directly. We can model it, we can simulate it, we can argue about it, but we cannot observe it. This is not a temporary limitation, it is permanent, and that permanence changes the emotional tone of discovery. James Webb is not opening an infinite frontier. It is revealing a finite window surrounded by infinite unknowns. The galaxies Webb reveals are not markers of progress toward completeness. They are reminders of how close we are to the edge of what is knowable. This is where the scale of the universe becomes terrifying in a very specific way, because it shows that ignorance is not something we will eventually overcome. It is baked into reality itself. The cosmic horizon ensures that there will always be more universe than knowledge, more existence than evidence. And Webb's discoveries intensify this realization by showing us that the universe does not thin out near the horizon. It remains dense with galaxies, rich with structure, and full of complexity right up to the limit of visibility. There is no gentle fade into emptiness. There is no suggestion that beyond what we see lies nothing. On the contrary, everything suggests continuity. The universe does not end at the horizon. Our ability to know it does. This distinction is subtle but devastating. It means that reality extends far beyond our intellectual reach, not because we are weak or primitive, but because the universe is fundamentally uninterested in being fully known. This forces a shift in how we think about cosmic significance. We often assume that understanding grows outward, that each generation pushes the boundary of knowledge a little further. James Webb shows us that there is a hard boundary beyond which knowledge cannot pass. We can approach it, we can map it, we can describe its behavior, but we cannot cross it. The observable universe is a cage made of light and time, and we are inside it. This does not make science meaningless. It makes it humbler. It forces us to accept that even the most powerful instruments ever built will only ever reveal a fraction of what exists. And that fraction, Webb suggests, is already overwhelming. The universe we can see contains more galaxies than we once thought possible, more structure than we can easily model, and more history than we can fully reconstruct. And beyond it lies a universe that may be vastly larger still, following the same rules, building the same structures, and evolving in ways we will never witness. This realization strips away another comforting illusion, the idea that the universe is ultimately comprehensible if we are patient enough. James Webb is teaching us that patience has limits, not because time runs out, but because access does. The cosmic horizon is not a challenge to be overcome. It is a feature of reality. And as we absorb this, the terrifying scale of the universe becomes not just a matter of size, but of separation. We are not small in a large universe waiting to be explored. We are isolated in a vast reality that will always remain mostly unknown. This is the emotional weight Webb brings to cosmology, because it forces us to confront not just how much exists, but how much will always be out of reach. As once we accept that the observable universe is a shrinking bubble surrounded by inaccessible reality, we must confront the most unsettling implication of all, which is that there may be not just billions or trillions of galaxies beyond our view, but entire cosmic histories unfolding without any possibility of connection, observation, or meaning to us at all, a truth that redefines isolation on a cosmic scale and brings the full existential impact of Webb's discoveries. When the full implication finally lands, it is not awe that settles first, but a quiet vertigo, because the terrifying scale James Webb is revealing is not just about how much exists, but about how little of it will ever belong to us in any meaningful sense. And this realization crystallizes when we confront the idea that there may be trillions of galaxies, almost all of them forever unreachable. For most of human history, isolation meant distance measured in miles or oceans, barriers that could eventually be crossed with effort, technology, or time. Cosmic isolation is different. It is not a challenge, it is a condition. The galaxies James Webb is uncovering near the limits of observation are not simply far away. They are already receding into a future where their light will never reach us again, no matter how long we wait. These galaxies are not hidden behind obstacles. They are hidden behind the geometry of space-time itself.